Welcome everybody back. I would like to introduce Andrej Muhic, who is currently student Johannes in Vienna, and despite he spends a lot of time at university, he has a code that is running small places like Twitter or Bloomberg that you may know about. And his biggest specialty is cross-lingual machine learning tasks, I would say, not necessarily translation. It can have many applications. And I think it's a very interesting field that maybe not too much exploited, and we just let him introduce something.
Like David said, the talk will be about the cross-linguality similarity computation, but in principle that means that if you have two documents, for example in English and Spanish, so in two different languages, you would like to compute the similarity between them. So, and you would like to do for as many languages as possible. So there is some number, 100 languages. So these are all languages from Wikipedia, for example. And of course, it's not only about similarity, but also projecting, these documents in some common space. This is more than just similarity computation, because if you project the English and Spanish document to the common space, then everything that works for English will work for any language. For example, you can have Arabic language project to the same common space and do the categorization there that is available for English or for any language. So this you can exploit many things. You can explore the news bias and even more. So you can even have something like the event detection, so language independent event detection. And during my talk, we will look at some examples. So how did we apply this work to some Bloomberg use case, so some news agency use case, and at the end, how we applied that to the event registry use case. And we also look at a couple of live demos. So we will see applications live. So we'll be using these systems during my talk. So this is Newsfeed. So Newsfeed can be thought of as some kind of news crawler. And we are crawling the news in many languages. I think currently it's more than 40 languages. So you can have some publicly available news sources. And of course, this news is a little bit language biased. So that means that most articles, at least half of them are in English. And the second one is German. And I don't know, only 2% or even less currently in Chinese, for example. So the second one we will not be really interested in, but it's an additional layer that we have. So language and semantic annotation available only for a couple of European languages. So English, German, I think Spanish. So this will be the main component. So this is in fact my work now, and I have been working on this for more than 4 years. So we have a cross-lingual document leaking and categorization, but as I said before, this also enables mapping in the common space. So, and there is another demo, so News Diversity Explorer. So, and at the end, as a final example, we have this event registry. So this is event detection and topic tracking. And we will see how we can really exploit this cross-lingual function that we have on that use case. So here is example of the workflow. So we have some multilingual data feeds. So this is, for example, newsfeed. We go through linguistic processing, semantic annotation that is available, and this component is available for every language. So we have a cross-lingual semantic integration. That means, in principle, mapping in the common space. So, and this can be used, as I said before, in many use cases, for example, in language-independent categorization that we will show. So currently we are doing this only for 100 Wikipedia languages. You know, I will tell why. These are Wikipedia languages that are in principle of high enough quality and have more than 2,000 documents. But you know, Wikipedia is constantly growing, and now more than 130 languages have more than 10,000 documents. And what's what are the main properties of this approach? You know, of course, it has to be scalable. So we want to have efficient computation for a big number of languages. You know, adding to one language should not add to the complexity of the model much. You know, this should be just linear with number of languages. And also another important thing is this rapid training on a large number of documents. And in fact, this is achieved with some, I would say, numerical linear algebra techniques, and of course, even with these random projections, and that enables us to reduce the dimensionality of the data. You know, imagine a lot of if you have data mining people that don't know a lot about numerical linear algebra, they say, okay, I cannot have a feature space that is too large. You know, I cannot have a feature space that has, I don't know, 1 million words or something like that. But that, in principle, is not really a problem, because you can always use this random projection to reduce the dimensionality of the data, and this Johnson-Lindenstrauss lemma guarantees you that you get close enough vectors at the end. So the system has to be clean. You know, ideally that means that if you add the new language, nothing should change. So you compute that, and no additional changes in the system are needed. So this is, you know, the example. How can this be used in some, at the end, really big pipeline? So we have a stream of news. So this is newsfeed and blogs. We do this cross-lingual article matching. What does this mean? For each article that comes in, we have a stream of the documents for 1 day stored for each language. And for each language, we compute, I don't know, top 100 articles. And in some sense, that enables us the detection of the similar articles independently of the language. And that, of course, then can be used to decide to which cluster we map each document. So this is this cross-lingual cluster matching. We can use that like some cutoff function that we don't go through all the documents, but only through most similar ones. So this is our goal. So we would like to, like I said before, learn this cross-lingual function. And here's one example. We have one English document about data mining, and here's the Spanish document about data mining also. So all the timing that I'm listing there is for my laptop. This is for my laptop. So similarity computation and categorization, it should take less than 20 milliseconds. And comparing to 1 million documents shouldn't take more than 1/4 a second. So, and this can be done on my laptop. Even, you can even improve these numbers a little bit if you really try hard to exploit the structure. So the model, I will not complicate things. I will just present the outline. So mainly we are not doing almost any pre-processing. So we just remove rare words, apply this term frequency, inverse document frequency weighting, and do the normalization to, reduce the bias that is implied by, the length of the document. So if we would have one document that we would copy the same document 10 times, if we wouldn't apply the normalization, that document would add more, at the end. So this is this standard back of word space. So we are mapping this text to sparse vectors. So that means, for example, data is the word of the number 100, and frequency, I don't know, here is 1, but it could be 5 or something like that. And we do the same for the other document, and we do the mapping to this common semantic space, as I call it. So that means that at the end, the vectors will live in the same space. So, and this nice property enables us to do the things that are available for one language independently and as many languages as we have. So here we are using only 100-dimensional space. We will see why. I have some results there. But at the end, that means that computing the similarity is only, product of scalar product of 500-dimensional vectors. So it's really fast. The most expensive thing is projecting this. And all these errors that I'm showing here, these are all linear mappings. That means we will be using, numerical linear algebra libraries to speed up the computation. If you are doing the computation here in the wrong way, you can really lose a lot. You wouldn't believe it, but for example, if you have the row major data, so data is organized by rows, and you are assessing the data by columns, when you are multiplying the matrices, that means that you will introduce quite a trade-off. So your computation will be 100 times slower than before. So, and a lot of people are doing that, sadly. So this is our corpus that we are using really a lot. The advantage of this Wikipedia corpus is that it's freely available. Everyone can download it. The only problem is this strange syntax that is not well defined, so Wikipedia syntax that you have to parse. But that just means that you could imagine, here is a data mining article. On the left, if you remember the Wikipedia, we have the list of related articles in other languages, and we are using that as cross-lingual matching. It's not perfect. It's not the translation, but if the size of the data is large enough and of the high enough quality, we can get something. And this turns out to be, after some processing, for 100 Wikipedias. But I can warn you that it doesn't mean that you will have better results if you have more articles, because you can have some really strange languages. For example, Varai language that has, I think, currently more than 1 million documents, but at least 95% of them are stubs. In fact, I would say they're completely obsolete for the computation. And you have to remove that, otherwise you just introduce a lot of noise. So the other possibility would be this Unopar and quite a lot of other corpuses, for example, Acquis Communautaire. And in fact, these are the exact translations, because these are the transcript of the European Parliament. So now I will go to the demo. So cross-linguality, the question is, again, how to operate in many languages. So, as I said before, we would like to map all the different documents in the common semantic space. So here is some trade-off. So machine translation is expensive and slower than this computation. So that would mean that you would have to pay Google for this, or you can use, for example, my approach or our approach, and reduce this to, I don't know, only to 100 most similar articles, and you only translate that. So maybe it's best if I now show the demo. So we'll see what can be done. So the demo is, in fact, it's quite simple. So at the left and right we have documents and in different languages, and we can just click report to compute everything, and now I can try to explain. So this is the similarity score. So these articles were, in fact, translations obtained by Google Translate. So the similarity score should be close to 1, that's okay. And, for demo purposes, I also display these keywords that add the most to the similarity. For the demo purposes, we almost use this back and forth space because it's easier to explain what's happening. So it's not perfect, but, it's good enough. So, of course, these documents are now mapped in the common space, and we can do the categorization. This is just categorization using DMOS, so the openly available categorization. And you see that it works quite well. We categorize this was direct translation, and even the summary of categories is almost exactly the same in this example. So this is one possible usage. The other one would be like this one. I hope that this works. So, for example, here let's magnify this a little bit. So at the left side, this is the Bloomberg use case that we will talk about really soon. So here we have two streams. On the left we have a Bloomberg stream. We can retrieve the documents by the index, and at the end is this newsfeed stream. I think it's for 1 month of articles or something like that. And the typical usage of this would be, so compute I don't know, I have something. Compute the most similar document in this newsfeed stream to this current Bloomberg document. So this computation was done live, and we can see, okay, what did we obtain? Okay. So this is the similarity score, and this was the article. So the German article, so we have only a German newsfeed there, and this is the German article that is most similar to this one, and these are these similarity scores. So this is the typical application that is done, in this X-Link service constantly. You could imagine you have a stream of documents, 1 million per day, documents come in, you have to compute all the similarities, sort the similarities, and return the top ones, and also do the categorization. So, particularly, we will look at this demo again. Okay, so here's just the output. So this service, in fact, enables the language-independent computation. So you could also get the language-independent representation, which is just 500-dimensional vector. So here, the current top 100 Wikipedia languages. Also, I think Galician should be there. Okay, of course it is. It's here, and I forgot before, but we can also try this demo. Okay. Chinese. Okay. So I pasted some text about the football from the Galician Wikipedia and Galician. Okay. We can try this. There was less information and of less quality than, for example, for English and German. That this similarity core is a little bit biased. But we still get the meaningful results for the categories, and you can always look at these keywords if you obtained, so to know if you obtained the meaningful result. So of course this works independently of the language. For example, now we have English Chinese. If we know Chinese, we could see that this is the right thing, but you can cheat a little bit, and you can always put these keywords in the Google Translate and see that you obtain the right thing. Okay. So this was, I already showed that. So we have everything there. And here is one interesting use case. This is the Bloomberg use case. So this is, I would say, the news recommendation use case. So you could imagine you have, the goal would be you have one German user, one German user of this Bloomberg interface, and you would like to recommend the most similar articles to the English article that he's currently reading. So it turns out that usually users prefer, the articles in their native language. Even German people, Spanish people, the statistics tells you that. So this is too small, but this, this cross-linguality was used to recommend this one. It was one of the features that enabled the recommendation of these local German articles, and it worked quite well. The biggest fear of this Bloomberg was, what happens? User gets there are the recommended articles, and they are paid by the time that user spends on their page. So the user will click, will the user ever come back? Will the user spend more time or less time on this web page? And the answer is, it will stay exactly the same. User likes to come back to this web page because he likes the quality of this information at the end. But the saddest thing is the frequency doesn't increase at the end. So at the end, Bloomberg didn't decide to use that. But it doesn't hurt you. At least you know that it doesn't hurt you. So this is other use cases for this Slovenian agency. So they would like to know how these their articles that they're writing, how is this disseminated around the world? Are some publishers stealing their articles, just translating them to English? Do Slovenian publishers use their articles? And of course, the answer is yes. So, and this should be done automatically and in a better way than it was done before. So, and here is, another important example for them. So they would like to have a story tracking. That means story started in Slovenia, and you would like to have, in some sense, a graph how this information traveled around the world. So, and you can obtain this by this cross-linguality similarity function. And at the end, there was some nice interface built for them that they could use, and they could see the spread of their articles. So now, these were the use cases. We will come back to that if there will be time. But now I would like to tell you something about, linear algebra and why was this approach chosen, for this exact use case. So here we have I call it hub proxy structure of the English language. So this is how well are the other languages aligned with the English one. So you have some language IDs. And you can see that number of articles connected to English almost exactly corresponds to total number of articles. And the reason is simply that usually the article is written originally in English and is then spread in some way or translated in the other languages. So that means if we will go through this English language, we will keep almost all information. For example, we will also see the case when we have almost no direct information available. For example, if you would choose Slovenian language and the Hindi language, and you would look at these related articles given by Wikipedia, there would be almost no of them, 100 or something like that, so not enough information anyway to do something meaningful. So this is approach, now written in a mathematical sense. So again, everything is a vector space and everything is linear. That's not a coincidence. I like linearity because I'm an expert in numerical linear algebra and I know how to exploit that structure. So these aligned bases, or you could say these mappings to the common space, these mappings will be always linear, and at the end this will be the vector space, and you could use many different similarity functions, Euclidean distance, cosine similarity, whatever you want. So here's, to just get an idea what's the multilingual topic. So for example, this was, one topic vector. These topic vectors are now, only 500 dimensional vectors with some components, and here we display the components at the end when we map this back that corresponds to the highest weight. So here would be one topic in English, you could say that it was about church. So we have one in English, one in German, and one in Slovenian. So, but at the end, this is just to show that something right is happening, because you must be careful, because these weights at the end are not necessarily positive, but can be also negative. So that's why you have to be careful. So I will just go through the work that was already done. So my first implementation that was done for Bloomberg used this cross-lingual latent semantic indexing. We will show the idea of that on the next slide. So the other idea was principal component analysis. And these ideas were, of course, already available. This was our idea, so we call it star canonical correlation analysis. So in some sense, that means that we are only optimizing these correlations with the one language, with the hub language. So we are only optimizing correlations with the English language. So initial system was done in MATLAB, but we switched to C++. So, and because of the modularity and the speed up, and we are using these high-speed numerical computation libraries like BLAS. The most known openly available is OpenBLAS, for example. So all this is already implemented. We can have everything, n-gram extension, word n-grams, character n-grams, whatever you want. So, and another nice addition to that was this language-independent DMOS classifier. But as soon as you have this mapping to the common space, everything is language-independent. So, and I must say that these approaches are, in fact, usually harder to compute and use than the last one. It's very simple at the end, and this works really well for Wikipedia. I don't know, for Europar, probably this wouldn't work so well, because we don't have this nice proxy structure. And in fact, this one is more robust and modular. If you're using the Wikipedia, we can handle these missing alignments that I was talking about, with, for example, Slovenian and Hindi language. We can also compare the languages that have no alignments. So that was before, but now I upgraded the system. There was more bookkeeping, so we needed to do the alignment every time, but now everything is really mapped to the common space. So, and the topic that I'm interested in the future are these graphical models, but now using spectral LDA. That means numerical linear algebra techniques about eigenvalue computation for symmetrical tensors to obtain meaningful results. So I had to update this, and that's why I also upgraded the system in last month. So currently Google Translation handles 103 languages, so we are not better than Google. Our approach now can be easily extended to these, I would say, 150 languages in Wikipedia. So I think more than half the memory requirements, so we can easily go to 200 if we would have the data. But the problem is at the end, you don't have the data for this. So we already talked about this. So demand, of course, some more applications are demand prediction, plagiarism detection, if some students copied some papers, finding events, and this finding event stuff, it will be the last stuff that I will talk about, because you can really see everything in the action at the end. So here's again this, and this is just, I think I have chosen the simplest example. So this is the process for all approaches. We are using these, as I said, the randomized techniques. The first step is to project your data. I don't know, you have, at the start you have 300,000 words, and then you would like to reduce the marginality of that, and you can do this using random projections. There are many reasons why you would want to do that. Many of these algorithms at the end involve some computation of the inverse of some matrix, computation of the Cholesky decomposition or related problems. And these problems can be numerically unstable. But if you apply this random projection step as a filtering step, that means that your space will be, I don't know what, 1,000 dimension, and you can do everything in a direct way. So computing an inverse of the 1000 dimensional matrix is an easy problem. So, and in fact, you don't need to optimize these regularization parameters that are usually used. And this is really, one nice step that enables you to do the rapid training. And of course, you get rid of this optimization of the regularization parameter. And the most important thing is that, all the mapping that you have should be, identity on the space that you are projecting to. What would that mean? If somebody knows, for example, this cross-lingual LSI, that would mean, so this is document matrix 1, document matrix 2, and document matrix 3. And these documents are aligned, so that means that the same column corresponds to the same document. So fifth column in the English one should correspond to the fifth column in the Spanish or something else. So we have this. And we just compute this singular value decomposition, but I must warn you, we pre-applied this random projection step, so these matrices are not of a large dimension at all. So, for example, this could be, I don't know, if we had this 1500 dimensional space, and computing this is now much easier at the end. So, and these are the topics, and usually if you look in the literature, they usually say that here you just compute the transpose of the matrix. That would be the right way to do it if this matrix would be orthogonal. But this matrix is orthogonal as a whole. If you split it by blocks, this is not an orthogonal matrix. And just using this, you can get additional almost 15% increase in the accuracy if you are using the right mapping, And this mapping should be identity of that space. So, you just imagine if there wouldn't be this inverse, that would be identity on the space spanned by the columns of this U1. So here are some results of this. So this is, in fact, the measure of the accuracy, this average mean precision score. So probably everyone knows that. So, you have one document, you have, the corresponding document, for example, in another language. And now you rank that these corresponding documents is the sixth one coinciding the similarity, and that means that the inverse rank would be 1/6. So, and the results that you get there have a really high, this average mean precision score. So most of the time we get the right pair, but we wouldn't like that we get the right pair every time. Why? If there would be one, for the practical use, this would be really bad, because we are using Wikipedia, and matchings in Wikipedia are sometimes completely wrong. You can have two articles that are not related at all. Somebody made a mistake. They are trying to, correct this all the time. But if you didn't detect that and then you're optimizing against that, you're, optimizing against the complete rubbish. So you wouldn't like to obtain, precision of one, because that means that you overfitted to your data, that is quite noisy. Wikipedia is noisy. So, okay, this is a cutoff of 400, but you can also see that some sense this base vector, these topics, the topics about the church that I displayed, so 500 dimensional vectors, and you can see if you increase the dimension of your space, your precision score increases. But you have the cutoff here about 500, and that's the main reason is the noise of the data. If you try the same approach on the Euro part, you must be careful. There is almost no noise there, and you can expect that this will increase up to, 1,500 or something like that. So you should choose number of the topics corresponding to the data set you are using. So of course, if you have more training documents, if you have more data, you can exploit that. And that's why, in some sense, number 10,000 was chosen as a cutoff, because 10,000 gets us the minimal results, and if you have 10,000 articles in the Wikipedia, that doesn't mean that these articles are all useful. So typically that would mean that only, 4,000 of them are useful, because smaller Wikipedias usually have smaller quality. So, and this is this so-called hub language approach. As I already told, here's an example with only few alignments, or you could have an example with no alignments. And we can use this, for example, CCA, canonical correlation analysis. Okay, this is some typo, so language independent space. So, but that means, if you do canonical correlation against, for example, English and German, and English and Slovenian, this will be the different English spaces. So we have to correct that. So using some proxy matrix. So this would be the final picture. So here is one possible approach to dealing with missing alignments, map to the common space, and you could always imagine, okay, I will go here through Slovenian to English and go here using the proxy matrix to be able to come here. But we can do it even better, because if we would do it in this way, that would mean that we would have, and choose two possibilities of these proxy matrices. But at the end, there is a better approach. So we have different languages, and for example, on this picture, I think I can better show it on this picture. For example, we would do it like this. So for example, here, somewhere here is German space, and we go like this. So we go through Slovenian space to this English space corresponding to Slovenian, and using the proxy matrix, we go from this English space corresponding to Slovenian to the English space corresponding now to the German one. And if you do it like this for every language, that means that this space at the end will correspond to the English space of the English-German pair. So that means that we need only, if you have 100 languages, you only need 100 proxy matrices at the end. And this reduces memory requirements a lot. So of course, this also reduces the topic drift because of this sometimes very bad pairwise alignment. And this is the possibility, the only, the reason that this works is that we are using Wikipedia. This is well linked to any other language. So this is the current approach. So just to summarize, so we are estimating everything only against the English. We found these initial subspaces using this truncated SVD decomposition, using these randomized techniques. And we ignore these non-hub covariances, because in some sense, as we've seen, for example, for Slovenian and Hindi, that this is just noise in the data. So, and at the end, we have no problems with these poor estimations for language pairs. it's true we discard some information, but in this case that means that we discard information that is usually the noise. So this works well. So, and now we only need this one proxy metric for each target space. So this is the summary of everything. Now we really have the common space and everything is language independent in this space. So I think we can skip this. So this was, in fact, this was the old approach. So you can thought of this as this cross-covariance matrices with the English. You know, you just put them together, do the random projection, compute the SVD to reduce the dimensionality of the data, and then you find these strongly linearly correlated subspaces. And because we are doing this only this cross covariances using the English space, that means that our problem at the end is just the eigenvalue problem, and this is not so expensive to compute and has an advantage over the problem when we are optimizing all the cross-covariance matrices, and because that problem is in fact NP hard. So that's, in fact, this is the only way to compute something meaningful in a short time. So for example, this is the report using this method, the old method. The new one is a little bit better. So maybe we can just go to the picture. So here we can see the sizes of the line sets in 1,000, and here we have the retrieval score. And you know, for example, Hindi and Piedmontese is a minority language in Italy. Had zero alignment when we started this experiment, but using this we can still get meaningful results. So now to conclude, I will only show the final demo. To explain the demo, we need a little bit of the background. So that was the Bloomberg phase, Bloomberg use case that I was talking about, how to relate to newsfeed streams. And this can be done, you know, mapping to the common space in one stream, mapping in the common space to in the second stream, and then computing the similarity against the articles. And usually we are using time window, it's 1 day, and to consider only the most recent documents, because usually you wouldn't like to have documents that are, I don't know, for example, 1 month old. They're usually not relevant for the news. So this is the final picture of the system. Like, this is my design now. You could say that you have, I call them circle buffers. You know, you have documents stored per rows, and in fact they're stored in such a way, you know, if you have, for example, these documents could live on one server and they are stored row-wise in one big, I would say, buffer. And here's just a marker that separates English and German. Why is this good? You know, at the end we would like to, one document comes in and we would like to compare this document against all these articles here. So if we have data organized in such a way, that means that we have to do only one metric multiplication, compute all the similarity, and sort the blocks at the end. So as I said before, for example, here you can have one easy speed up. For example, instead of the doubles, you can use floats to halve your memory requirements, and of course speed up the computation by the factor of 2. And the process is like this. You get the job to assign to this server. So this is usually just a batch of the documents. This central server delegates the documents to these servers that have appropriate languages available. And for example, we have here is Spanish documents. It will be assigned to this. If it's an English one, it will be assigned to this. These documents are projected, this 500-dimensional vector is obtained, and it's returned to the central server, and central server then can return the documents to all local servers, and we can compute the similarity in a fast way. So doing the block-wise computation pays out, maybe, why? Some part of the picture is missing, but we will survive. So, this is just the computation. It's surprising what you can do using just block computation. And the reason is why it's simple, because if you're doing the block computation, you can use the speed of the cache. So the memory is much faster, and you can reuse the data in the cache. So if you have only one document, on my computer, it costs 0.3 of a second to compute the similarities against 1 million documents. And for example, if you would use 128 documents, that would mean that this number 0.3 reduced a lot. So how much faster, you can see, a lot faster. This computation is a lot faster. So 15 times faster, something like that. Then this, just by using these block size. So it's surprising, but this can really speed up the computation. Just using the laptop, introducing that, you can optimize things if you know what to optimize. So I will only show the demo. Okay. So here is this final demo that is using a lot of this functionality. So this is the event registry. It detects the events all over the world. So it's collecting these articles from the newsfeed. It's clustering them, doing semantic analysis, time analysis, sequence analysis, and a lot of things. And here is this gravitational wave, that was, they confirmed that gravitational waves should exist. And these are all the events pertaining to these gravitational waves, and these gravitational waves was first detected on the same day that it was published. So it looks like this. I hope everything works, because internet is a little bit slow. So this was the first article, and these are the articles in the clusters. If there are some picture, also picture is displayed. So we can see that there are a lot of articles about this. I think more than 1,000, and this is pretty meaningful data. So these are articles in all languages. So most of them are in English, but we also have some Catalan articles, so Catalan news sources, and we also detect that. So if we go on the main page, we can see in fact the system as it is working. I think the connection is too slow. It's really a shame. There's a lot of JavaScript in the data passing, but I hope the map will be short. So the article comes in and it's mapped to the one event, or new event is created. And can you see articles coming in, Russian articles, Spanish articles, and the corresponding location, geographical location. There is a lot of events already in the database, more than 4 million. Here is number of news sources and the number of categories that we are categorizing to. So the interface is quite nice. So everybody is of course welcome to try it. There is also API for using this X-Link service, but I didn't put it here because I have to update it, because I changed the approach. Okay. And that's all for me. So thank you for your attention.
Any questions for Andrej? So I have a question. I mean, you have these demos which are kind of synthetic. Where do you see the applications of which, what's the application of which for public use? I mean, we see this currently, which is basically this is an algorithm that runs cross-lingual documents. So what applications do you have in mind for making that available properly? So basically, what industry? On what industry?
So this event registry is, explicitly built for the news industry. So New York Times, whatever, even Bloomberg. So if you have news, you would like to detect the events, you would like to react on the events or something like that. That approach, detecting the events, but it was also used on Twitter, but there is much harder to detect proper events. Because, the people can post the wrong information intentionally. And even something like this, we tried using this on Twitter, but it's completely unreliable because someone that knows that you're using this can destroy your efforts completely. He just publishes something, people start spreading that news, you detect that this is an event, and if you act on this, it's dangerous. That's now, no one, in fact, is using Twitter, for detecting financial events, because the potential damage is much worse than, the profit. But for the public use, you could have, for example, a service for the plagiarism detection, automatic, we even have, the collection of all the articles that you have, and you can automatically see, someone from China used your material, probably used material, and you can take a look, you can translate that. So there are, countless uses of that. And of course, one use would be to have this, like some cutoff function. You have some data, it's, I don't know, couple of million articles, you just compute the top ones, and you would like more detailed information, and then you can pay Google. But you don't have to pay Google for every article, but just for the most similar articles. That would be another use case, for example. And in fact, that's the approach used in the event registry. So you can do, some computation of these clusters in completely different way, but you have this similarity scores. You could also have this language independent representation, and you can use that, I will not consider all these articles for this cluster, but I will only consider, 10 top ones, 100 top ones, and compute, all the complicated things only for that, instead of, I don't know, 100,000 articles or something like that. And this is, from our point of view, this is for free, because we store all this data, I forgot to mention, the data that is coming in, I also return the data, and all that data is available to every user of the newsfeed. If you have the access, to the private data of the newsfeed, or even public access, if the documents were public, you can take a look. Okay, this was the article with this ID, these are the top similar articles. You don't need to compute this yourself, and you just consider that article or something like that. So, yeah.
Thank you, Andrej.